Hello and welcome to this video lesson on variable oxidation states of transition metals with specification reference 3.2.5.5. And our learning objectives today are, firstly, we want to know what do we mean by variable oxidation states of these transition metals. And then, what are the three reactions of the vanadate 5 ion, that's a vanadium molecular ion. What are the three reactions of that ion with zinc to form vanadium of the oxidation states +4, +3 and +2? Then we want to have a look at how does the pH of the solution and the ligand affect the tendency of the transition metal to be reduced. And then what is the chemistry of the Tollens reagent reaction, which you might be familiar with, to detect for aldehydes versus ketones. What's the chemistry behind that reaction? Okay, there are four questions we want to answer. And let's start off with reminding ourselves about variable oxidation states. Yes, what do we mean by variable oxidation states? Well, from an earlier video, you'll remember that transition metals can be of different oxidation states, and the most common example probably is iron, which can exist as an iron 2+ ion and an iron 3+ ion. So we've got two different and therefore variable oxidation states of iron, and that's what we mean by variable oxidation states. And these reactions are redox reactions. So if, for example, we're going to go from Fe3+ to Fe2+, then that reaction there is a redox reaction because the iron 3+ has gained an electron, whereas if it goes in the opposite direction, that would be an oxidation reaction. So for the redox reaction, the 3+ to 2+, something else must have been oxidized, and that's why it's called a redox reaction. Now you need to know about the various oxidation states of the transition metal vanadium. And here we have all the different oxidation states of vanadium. Vanadium V. And at the top there we've got +5, so the vanadium in this VO2 ion is going to be +5. We want to just work out to check that. We know that oxygen also always has two minuses, and so for the oxygen we've got two of them, so there's four minuses there. So there must be 5 pluses on the vanadium because there's a net positive for the molecule as a whole. Okay, so the V in VO2+ is +5, and that appears as a yellow solution. Whereas VO2+, so that's one vanadium, one oxygen, but 2+, that's +4, and that's blue. Whereas V3+ is green, and V2+ is violet. And while we're at it, let's just name this ion here. This VO2 1+ ion is called the vanadate ion. So now we're moving on to three reactions involving the vanadium ion. Three different vanadium ions, in fact 4 different vanadium ions. The vanadate ion, you'll remember from the previous slide, is the VO2+. Not to be confused with the vanadium 4 ion, which is VO2+, and then this one is just V3+, and this one is V2+. So what we've got to do is we've got to start off with our vanadate ion, we've got to end up with our V2 plus ion by means of 3 different reactions. And here is a reminder of the colours, so let's just label them. We've got our vanadate ion on the left, which is yellow, VO2 plus. We've got our VO2 plus ion, which is blue. We've got our V3 plus ion, which is green, and we've got our V2 plus ion, which is violet. And the 3 reactions we want to study are this one here, and this one here, and this one here. So let's label them 1, 2, and 3. They're the 3 reactions we're going to do, and why not start with the first one? So we're going to start off with our vanadate ion. And we're going to end up with our VO2 plus ion. And let's change colour and label the oxidation states. So this is an oxidation state of +5, and this one here is +4. So if that is reduction, then something else has to be oxidized. And the thing that is oxidized actually is some zinc. So we are going to add some zinc in acidic solution because the hydrogen ions help the reduction of the vanadium ions. And so if we have reduced our vanadium, we must have oxidized our zinc, and when zinc gets oxidized, it gets oxidized to zinc 2 plus, and the hydrogen ions have facilitated the removal of one of those oxygens. See, notice there are 2 here, only 1 here, and so one of those oxygens is going to react with 2 hydrogens to make a water molecule, facilitating the process. So a little mistake here, that should be 2 hydrogen ions. Rather, not 2 hydrogen ions. In order to balance all this, let's do our balancing in red. In order to balance this, we're going to need 2 VO2s, and we're going to make therefore 2 VO2 pluses, and we're also going to make 2 water molecules. So that's our first reaction, and that has gone from vanadium 5 plus to vanadium 4 plus, and in the process gone from a yellow solution to a blue solution. So next, let's have a look at going from our blue solution of VO2 plus, in which the vanadium is a 4 plus oxidation number, to our green solution, in which our vanadium is 3 plus. So we've got our VO2 plus, which we can, let's just draw a little light blue line from here to here. So we've got our VO2 plus, which is our light blue solution, and we want to make that into V3 plus. And we need some more zinc to facilitate that oxidation, so let's just check our oxidation numbers first to make sure we are oxidizing vanadium. This VO molecule is 2 plus, but as you know, our oxygen is going to be 2 minus, and so in order to make the whole thing 2 plus, this needs to be +4. So +4 minus 2 is +2, so that all works. And the oxidation number of this is easy because it's just +3 as written there already. So we are reducing the vanadium in VO2 plus from 4 to 3. So we need something that is going to be oxidized, which is also known as a reducing agent, of course. And that's again our zinc, also in acidic solution. And when our zinc gets oxidized, it's going to turn into a zinc 2+ ion. And in the same way as this oxygen has been removed from the vanadium, it is going to be removed by reacting it with the acidic hydrogen ions to make water molecules. So there's H2O there, just as before, right? And as before, we need to balance that, and so we need 2 water molecules there. We're going to make 2 V3 pluses, and therefore we need 2 VO2 pluses. And that's our second reaction. That's gone from blue to green. And then thirdly, we have to go from green to purple to get all the way to vanadium 2+. So our third reaction is going to start with our V3+ ion. Drawing a little light blue line from here. And we are again going to reduce that, this time from V3+ to V2+. And we're again going to use some zinc to do that. So our reducing agent is zinc. So reducing agents are oxidized. And when zinc is oxidized, it gets oxidized to zinc 2+. And that's all balanced already. If we just add 2 and 2 here. So that's our third reaction, going from a green solution of V3+ to a purple solution of V2+. And they're the 3 reactions that you should be familiar with. And what we move on to study now is how much does the vanadate ion, for example, want to turn into the VO2+ ion. Indeed, how much does the V3+ ion want to turn into the V2+ ion? How do we know whether it is inclined to do so? And if so, how do we quantify that? That's the next slide. And the answer to that question, it is the redox potential, something called the redox potential, that measures how easily the ions or atoms are reduced. So just to give an example, we reduced our VO2+ to a VO2+ ion, and we were interested in how much does that want to happen, and it's the redox potential that measures the tendency of that to happen. And you're familiar with redox potentials already, but you know them by the term electrode potential. And they're the same thing. So the electrode potential, or the redox potential, tells you how easily the ions are reduced to a lower oxidation state. So more examples here. We've got, looking at the bottom one first, we've got a copper 2+ ion. So that's 2+ going to a copper 1+ ion, so that's a reduction reaction. All these tables are written with the reduction reaction as the forward reaction. And that has a positive electrode potential, which means it's quite likely to happen. It does want to happen compared to the standard hydrogen electrode. Whereas in the first example, when you're trying to make a chromium 3+ ion go to a chromium 2+ ion, you're trying to do that reduction reaction. Actually, the negative sign there says that it doesn't really want to happen. It doesn't want to happen. It would rather really go in the backward reaction compared to the hydrogen standard cell. So that's a quick reminder on electrode potentials and their synonym redox potentials. And what we're going to do now is learn about how the redox potentials are influenced by things like the pH of the solution and what ligand is involved. Okay, so this question phrases that little challenge for us quite nicely. So we're looking at the pH and the ligand and seeing how those two things affect the tendency of a transition metal to be reduced. So tendency of a transition metal ion to be reduced is the redox potential. So when we're talking about electrode potentials and standard electrode potentials, of course you'll remember that we use standard conditions to make the measurements, of course, and our standard conditions involve 1 molar solutions, for example, and the solutions are in water. Now our ligand may not be water, so for a standard electrode potential the ligand is water, but for a redox potential, if we've got a different ligand, then our redox potential is going to be different to the electrode potential, which uses water as the ligand. And also the concentration might not be a standard 1 molar concentration, it might be a different concentration. So let's first have a look at the effect of the ligand. So the ligand. So in our let's take a V3+ example. So V3+ is going to be coordinately bonded to water molecules when we're measuring standard electrode potentials. So we would have a water molecule making a coordinate bond with a V3+ ion, and in order for that V3+ ion to turn into a V2+ ion, it's going to make again a coordinate bond with some water molecules, so these bonds, these bonds here are going to be broken, and these bonds here are going to be formed, and that affects the electrode potential of this reaction here. Now, if instead of water ligands we used, for example, another ligand, let's call it a chloride ion ligand, then these bonds, the coordinate bonds that are broken and made, are each going to be of different strengths, and so that will either increase the electrode potential or decrease the electrode potential. So that's all we're saying. It's quite simple. We're just saying that the redox potential, which is the inclination of V3+, in this case to go to V2+, the redox potential might be different from the electrode potential if the ligand is not water. It could be higher, it could be lower. That's all you need to really understand about that. And so that leaves us with the effect of the pH of the solution on the redox potential. So the effect of the pH on the tendency of the transition metal ion to be reduced, or the redox potential. So first of all, let's just remember that when we're measuring the standard electrode potential, we're using neutral solutions, whereas when we're talking about redox potentials, we might be acidifying this solution. So let's have a look at an example to illustrate it. Let's take our VO to 1+ ion, and let's reduce that to our VO2+ ion. So we've gone from vanadium 5+ to vanadium 4+. And what helps that reaction is the presence of 4 hydrogen ions, because basically we've got to rip off one of these oxygens from the vanadate ion and turn it into and give it somewhere to go. and we facilitate that by adding acidified solution to, i.e. hydrogen ions. So we'll just balance the charges like so, and we will make water molecule. So the pH, the presence of hydrogen ions, has facilitated that reduction reaction, and that's what normally happens. Normally when transition metal ions are being reduced, that reduction potential is higher if there are hydrogen ions present. So let's just write that down. Usually the reduction of transition metal ions is facilitated or helped by H+ ions. And just for completeness, let's balance our equation. So we need a couple of van der Waals ions, and we make 2 of those and 2 of those. So that's balanced if doubled. Let's look at another example. This example where we're making hydroxide ions. So let's start off with the chromate ion. All right, so we've got Cr042-, and we're going to reduce the chromium in that to chromium hydroxide. Chromium hydroxide is like this. Let's say precipitate. And so you can see that our oxidation number of chromate here is going to be 3+, whereas our oxidation number of chromium here is 6+. So if it's going from 6+ to 3+, we'll need to add 3 electrons. We also have to balance the water, so we'll put in 4 water molecules here, and we're going to make 5 hydroxide ions there. And so what we're saying is that because this reaction makes hydroxide ions, if you acidified that solution by adding H+ ions, you would basically suck out those hydroxide ions, making them into water molecules. And according to Le Chatelier, of course, that would prompt more of the forward reaction, i.e. more of the reduction reaction, going from chromium 6+ ions to chromium 3+ ions. So in the same way as we did before, we can say that the addition of hydrogen ions facilitates the reduction of transition metal ions. And that's the same as saying the redox potential will be more positive in more acidic solutions. So we can write that down as well. The redox potential more positive in acidic solutions. Saying the same thing really. So hopefully that's answered our question that we started off with. And what we'll move on to now is the tolerance reagents and the chemistry behind it. And here's the question we want to answer. What is the chemistry of the tolerance reagent reaction with aldehydes and ketones? Well, you may remember already that tolerance reagent uses silver, and silver is a transition metal that's most often found in the 1+ oxidation state, and actually it's quite easily reduced back to its metal form as an atom by accepting electron. It likes that to happen, and our standard electrode potential for that reaction is quite high for a metal at 0.80 volts. So it really wants to happen. Silver ions quite like being silver atoms. And we prepare our tolerance reagent by starting off with some silver nitrate. So we've got silver nitrate, aqueous, so we've got silver ions, 1+ ions, and nitrate 1- ions, all in solution. And what we do is we add just enough ammonia solution to make a complex with the silver ions. So you get a silver ion in a complex with 2 ammonia molecules, like that. Ammonia molecules are neutral, so the complex stays as a 1+ ion, and that then is ionically attracted to the nitrate ions in the same way as the silver ions are attracted to the nitrate ions. So this is the complex here that is the tolerance reagent, and when we add it to aldehydes we get this silver mirror effect that's shown in the diagram there. And the reaction that is involved is, starting off with our aldehyde. Let's write our aldehyde like this, and then we're going to add some tolerance reagent to it. So we've got our AgNH3 2 all in a 1+ complex, and we need 2 of them, and we also need to do that in alkaline solution. And when we do that we get this, we get silver atoms being formed. So we list those as silver solid atoms, 2 of them, and of course we're leaving 4 ammonia molecules on their own, or at least dissolved, and a couple of water molecules. So that's our reaction that happens to create some silver, which you see as a mirror effect when you do it, when you add it to the aldehydes. However, when you add it to ketones, it can't oxidize the ketone, so it won't react with them, and you won't get any of this silver to give you the mirror effect. And that's the chemistry behind the tolerance reagent reaction with the aldehydes. And it's listed here in this topic, I suppose, because we've got this reaction going on here, which is where you've got a redox reaction going on involving the silver 1+ ions going to silver solid ions. So that completes our video lesson. It just remains to check off our learning objective questions that we started out with. First one, what do we mean by variable oxidation states of transition metals? Well, we looked at vanadium in particular and saw a couple of molecular ions, including the vanadium element with +5 and +4 oxidation states, and we also looked at the V3+ and the V2+. So 4 different oxidation states involving vanadium, so we can quite confidently say that vanadium has variable oxidation states, as do pretty much all of the other transition metals. In fact, all of the other transition metals. And we looked at those 3 reactions to start off with vanadate ion, involving the 5+ oxidation state, and we reduced that first to the 4+ oxidation state, and then the 3+, and then the 2+, and saw the corresponding color changes. So we did that, and we looked at the pH of the solution and how that affected the redox potentials, and we generally said that if you add H+, then what that does is it leads to a redox potential increase, and more likely reduction reaction of the transition metal ion. And also the ligands involved, we noted qualitatively that if you change the ligand from water, then the redox potential will be different from the standard electrode potential, which you use is pure water. And then lastly, we had a look at the Tollens reagent reaction and saw how silver 1+ ions were reduced back to silver atoms, giving you a silver effect, which could happen with aldehydes, but not with ketones. So we looked at the chemistry behind that, and hopefully that was clear.